Welcome back to the Deep Dive. This is the show where we really try to unravel complex topics, get into the details, and hopefully give you some genuinely insightful nuggets. Tailor-made just for you, the listener.
Yep.
Today, we're diving headfirst into, well, the fascinating world of data preprocessing in machine learning.
Yeah, it's a big one.
It really is. You know how every great recipe, it starts with the right ingredients, right? And they need to be meticulously prepared.
Absolutely.
Well, in machine learning, your data is that raw ingredient. And how you prepare it, it isn't just important. It's absolutely vital.
Couldn't agree more. It dictates the success of the entire project, really.
Exactly. So we've gathered a pretty comprehensive stack of sources today, all drilling down into the powerful tools and techniques from the well-known Slurm library.
Scikit-learn, yeah. The workhorse.
The workhorse? Good name for it. And we're focusing on their practical application.
Yeah.
So get ready for some serious aha moments. Because by the end of this deep dive, you'll not only grasp why certain transformations are, indispensable, but also understand how these incredibly powerful tools, like pipelines, can streamline and simplify even the most intricate data workflows.
And what's truly fascinating here, I think, is how often real-world data is just far from perfect.
Oh, yeah.
It's rarely pristine. It's usually messy. We're talking about issues like, missing values, features that are on wildly different scales.
Right, like dollars versus a number of kids or something.
Exactly. Or non-numeric attributes, things like text categories that machine learning models simply cannot understand directly.
They need numbers.
They need numbers.
Yeah.
So the necessity of preprocessing, it isn't just about tidying up. It's about making that raw, often chaotic data truly amenable for training models.
Amenable. Good word.
Yeah. This ensures you get accurate predictions, reliable performance evaluations, and ultimately, trustworthy insights down the line. It's widely recognized in the industry that often maybe 80, even 85% of machine learning work is dedicated specifically to this part.
Wow, 85%. That's huge.
It's that foundational data prep and feature engineering. And the beauty of Scikit-learn, as we'll explore today, is its remarkably uniform API for these transformers.
Okay.
The fit transform and fit transform methods, they provide such a consistent approach. It makes them much easier to learn and use across a vast array of scenarios. It really helps bridge that gap between, messy reality and the computational power we have.
All right, let's unpack this then. Let's begin at the very beginning of our data journey. Before we even think about feeding data into a model, we often need to get our raw info into a highly structured numerical matrix form.
Exactly.
And this is where that initial crucial work of feature extraction comes into play, right?
Precisely. When your raw data doesn't already arrive as a neat, perfectly structured table, which, let's be honest, is often the case.
Right.
You need specialized tools to get it into that format. Take Dict Vectorizer, for instance.
Okay, Dict Vectorizer.
Its core function is to convert lists of mappings, think Python dictionaries, or maybe rows from a pandas data frame where you have feature names paired with their values.
Like age, 4, height, 96-point arrow.
Exactly like that example. Dict Vectorizer will intelligently transform that list of dictionaries into a numerical matrix. So age becomes one column, height becomes another column, filled with the corresponding numbers.
And suddenly it's something an algorithm can understand.
Precisely. It makes it perfectly ready for most machine learning algorithms, which fundamentally expect data in this structured matrix form.
Makes sense.
Then we have something called feature hasher. Now, this aims for a similar goal, getting a numerical representation, but it takes a very different high-speed approach.
High speed. Okay, tell me more.
Yeah, feature hasher is incredibly efficient and uses very low memory. Instead of building a traditional dictionary-like hash table to map features to column indices, which can get large,
Right.
it applies a hash function directly to the feature name and its value to determine its column index in the output matrix.
So it calculates the column on the fly.
Kinda, yeah. It uses hashing to figure out the column index. This significantly boosts speed and reduces memory usage. It's particularly useful for truly massive, very high-dimensional data.
Like text data. Millions of words.
Exactly. Think text classification problems, where you might encounter millions of unique words or n-grams. Feature hasher handles that scale really well.
Okay, sounds amazing. What's the catch? There's always a catch.
There is a trade-off, you're right. The genius of feature hasher is its speed and memory efficiency, especially for those huge data sets. But here's the crucial insight. It's pretty much a one-way street.
Ah,
Because it uses hashing directly to find the column index, you lose the direct link back to your original feature names. There's no stored mapping.
so you don't know which original feature ended up in which column.
Exactly. This loss of inspectability means you can't easily trace back which original feature led to a specific transformed column. And consequently, it lacks an inverse transform method to convert the transformed features back.
That could be a problem for understanding the model.
It can be a real headache, yeah. Especially when you're trying to debug your model or explain its decisions maybe to a non-technical audience or for compliance reasons. It's a classic example of that trade-off. You gain efficiency, but you might lose some interpretability.
Right, balancing speed against understanding. Makes sense. Okay, so let's say we've used one of these. Our data is now in that neat matrix format. What happens when pieces are just missing?
The missing data problem.
It's a notoriously common headache, right, in real-world data sets. It could be a blank in a survey, a sensor malfunction, maybe just human error during data entry. How do we deal with those frustrating gaps without just throwing away valuable information?
This is exactly where data imputation comes in, and it's an absolutely fundamental step.
Imputation. Filling in the gaps.
Precisely. The problem with missing values is indeed widespread. They can pop up for all sorts of reasons, like you said. Sensor failures, measurement inaccuracies, human error. The critical issue is that most machine learning algorithms simply cannot work with missing data.
They just crash.
Often, yeah. Or they throw errors. They demand that all features be present for every sample, and simply discarding rows or records that contain missing values. Well, that's usually not a great option.
Why not? Seems easiest.
Because it means throwing away potentially valuable training data. Especially if missingness isn't completely random, you might be discarding specific types of examples, biasing your remaining data. You can severely impact your model's ability to learn the true underlying patterns. So we absolutely need intelligent ways to fill those gaps.
Okay, so how do we do that intelligently?
Scikit-learn provides a couple of primary classes for this. The first, and probably the most straightforward, is Simple Imputer.
Simple Imputer sounds simple.
It is, relatively. This tool fills missing values based on specified strategies that you choose. You have several options. You can replace missing values with the mean of that column.
The average.
Right. Or the median, which is the middle value, often better if you have outliers.
Okay.
Or the most frequent value, which is useful for categorical data. Or even just a constant value that you specify, maybe 0 or -1, depending on the context.
So give me an example, like if I have daily steps walked and some days are missing.
Perfect example. If you use Simple Imputer with the mean strategy on that daily steps column, it would calculate the average steps for all the days where you do have data.
Right.
And then it would fill in the blanks, the missing days, with that calculated average.
Okay, and median if there were some crazy high step days.
Exactly. If you had a few marathon days skewing the average, the median would be more robust, less affected by those extremes. And if you had a categorical column like weather condition with some missing entries, most frequent would fill them in with sunny if that was the most common condition recorded.
Makes sense. Choosing the right strategy depends on the data.
It truly does. It depends on your specific data's distribution and, importantly, thinking about why the data might be missing.
Okay, so Simple Imputer sounds like a really good first pass, but it's still using a pretty broad column-wide average or median, right? What if the missing value isn't just any average, but really ought to be filled with something that makes more sense in context with the other values in that specific row?
That's a great point, because sometimes a simple overall average just isn't nuanced enough.
Right.
For a more sophisticated and context-aware approach, we have KN Imputer.
KNN, K nearest neighbors,
Yep.
like the classification algorithm.
Exactly like that. It leverages the same K nearest neighbors approach. Instead of simply filling a missing value with the column's overall mean or median, KN Imputer goes looking for the neighbor's closest samples, the most similar data points to the one that has the missing value.
How does it measure closest if a value is missing?
Great question. It cleverly calculates these distances based only on the features that are present in both samples. It intelligently ignores the missing values from the distance calculation itself.
Oh, okay.
Then, once it finds the K nearest neighbors, where K is neighbors, it fills the missing value with the mean, or sometimes median, depending on configuration, of that specific attribute from those K closest neighbors.
So it's like looking at similar examples to make an educated guess.
Precisely. Think of it like this. If you have a friend whose income is missing in your data set, instead of just using the average income of everyone you know, simple imputer mean,
Right.
you'd look at your 2 or 3 most similar friends, maybe those with similar jobs, education levels, locations, KN imputer, and use their average income to estimate your friend's missing income.
That sounds much smarter, more tailored.
It is. It makes KN imputer a much more nuanced and often more accurate imputation strategy compared to simple imputers' feature-wide averages, because it uses the inherent structure and relationships within your data.
Cool. Are there any other tools for missing data?
There's one more neat utility called Missing Indicator.
Missing indicator. What does that do?
This tool doesn't fill values. Instead, it returns a binary matrix, just trues and falses, where true values correspond to entries that were originally missing in your dataset.
Why would I want that? I thought the goal was to fill them.
Well, sometimes the very fact that a value was missing can be informative. The missingness itself might actually be a signal.
How so?
Maybe data is missing for a specific reason that correlates with the outcome you're trying to predict. For example, perhaps people who didn't report their income are more likely to default on a loan.
Ah, I see. So the pattern of missingness is data too.
Exactly. Some models can genuinely improve their learning process by knowing where the data originally had gaps. Missing indicator allows you to capture this information. This is particularly relevant when you use the optioned indicator, true within simple imputer or KNN imputer. That tells the imputer to not only fill the missing value, but also add a new Boolean column indicating whether that value was imputed.
So you get both the filled value and the flag saying it was originally missing.
Precisely. Best of both worlds sometimes.
Okay, this is great. So our data is clean, missing values are handled, everything's in a nice numerical matrix. But even perfectly clean numbers can still be all over the place, scale-wise. You mentioned that earlier, income in thousands, number of children in single digits.
Right.
And then we've still got those text fields we talked about, maybe gender, state name, which we converted to numbers, but models still need to understand them correctly. Here's where it gets really clever, I feel. How do we normalize all these different scales and types of features so our algorithms can understand and process them effectively without one type accidentally overpowering another?
Indeed. This is where numerical and categorical transformations truly come into their own, and it's crucial. Starting with numerical features, scaling is absolutely vital in many cases.
Why vital?
Well, imagine that income feature in thousands and the number of children feature. If you feed these directly into certain algorithms, the income feature, just because its numerical values are much larger.
Right, 50,000 versus 3.
Exactly. It might disproportionately influence the model simply because its numbers are bigger, even if number of children is equally or perhaps even more important for the prediction.
So the scale itself creates a bias.
It can, yes. Numerical features with vastly different scales can create several problems. For iterative optimization algorithms like gradient descent, which is the engine behind training neural networks and many linear models,
Okay.
widely varying scales can significantly slow down convergence. The algorithm might bounce around inefficiently trying to find the optimal solution, making training much longer.
And for other types of models?
For distance-based algorithms, think support vector machines, SVM, k-nearest neighbors, KNN, or k-means clustering features with larger scales can completely dominate the distance calculations.
But distance is just calculated from the numbers.
Exactly. A difference of 10,000 in income swamps a difference of 2 in children when calculating how far apart 2 data points are. This effectively makes smaller scaled features less impactful than they should be, distorting the model's understanding of similarity.
Are there models where scaling doesn't matter as much?
Yes, that's an important distinction. Tree-based algorithms like decision trees, random forests, or gradient-boosted trees are generally not affected by feature scaling
Why not?
because they make decisions by splitting on individual feature values, is income 50K, not by calculating distances between points in a multidimensional space. The scale doesn't change where those optimal splits occur.
Good to know.
Yeah.
So for the models that do need scaling, what are our options in scikit-learn?
Scikit-learn provides 3 primary ways to scale numerical features. First, there's standard scaler.
Standard. Sounds like the default.
It often is. Think of this as bringing all your numerical features to a common baseline. It adjusts them so their average, their mean, becomes 0.
Okay.
And their spread, or variability measured by standard deviation, becomes 1.
So it means 0, standard deviation 1, that's z-score normalization, right?
Exactly, that's the z-score. The intuition is that a value that was exactly average before scaling stays average, it becomes 0. And values that were, say, 2 standard deviations above the original average will now be exactly 2 on this new scale, regardless of their original units. Dollars, kilograms, whatever.
It's like putting everything on the same ruler, centered at 0.
Perfectly put. It aligns all your features along the same central point with the same spread, making them directly comparable in terms of their deviation from the mean. This is often the default choice, especially if your data roughly approximates a normal bell curve distribution.
Okay, what else?
Then we have min-max scalar. This transformer scales features to a specific range, most commonly between 0 and 1.
So the smallest value becomes 0, the largest becomes 1.
Precisely. The minimum value in a column gets mapped to 0, the maximum value gets mapped to 1, and everything in between is scaled proportionally into that 0 to 1 range.
When would I use that instead of standard scalar?
It's particularly useful for algorithms that are sensitive to the absolute scale or range of input features, like neural networks often prefer inputs in the 0, 1 or -1 to 1 range. It's also very common in image processing, where pixel intensity values often need to be normalized to a 0-1 range before being fed into a model. It ensures all features contribute within a very specific, defined boundary.
Got it. And the third one?
The third main one is max ab scalar. This transforms features to a range between -1 and +1. It does this by dividing each value in a feature column by the maximum absolute value found in that column.
Maximum absolute value. So if the range is -100 to 50, it uses 100.
Exactly. In that case, the max absolute value is 100. So an -100 would become -1, 50 would become 0.5, and 0 would remain 0.
Why is this useful? When would I pick this one?
This scalar is particularly well suited for sparse datasets that contain many 0 values. Think about text data represented as word counts, lots of zeros. Max ab scalar is useful here because it preserves the zeros. Standard scalar might shift them if the mean isn't 0, and min-max scalar might shift them if the minimum value isn't 0. Max ab scalar keeps zeros as zeros, which can be important for sparse representations.
Okay, so the choice depends on the data distribution. Normalish, maybe standard scalar. Need a fixed range, like 0, 1, maybe min-max scalar. Sparse data, consider max ab scalar.
That's a great summary. It often comes down to the data's characteristics and the specific requirements or assumptions of the machine learning model you intend to use. Experimentation helps too.
Right. Now, beyond these standard scalars, you sometimes need more specific transformations, right? Not just scaling.
Absolutely. Sometimes you need more specialized numerical transformations. This is where custom transformers, specifically the function transformer, come in incredibly handy.
Function transformer, what does that let me do?
Function transformer is really flexible. It enables you to wrap any existing Python function as long as it just applies a transformation and doesn't hold on to state between calls into a scikit-learn compatible transformer that you can slot into your pipeline.
Any Python function, wow.
Pretty much, yeah. This is incredibly useful for applying nonlinear transformations. A common example is using a logarithmic transformation, maybe using NumPy's np.log1p function.
Log1p. Why the 1p?
Log1p calculates the natural logarithm of 1 plus the feature value. It's useful because it handles 0 values gracefully. Log 0 is undefined, but log 1 plus 0 is just 0. And it's great for normalizing distributions that are heavily skewed to the right.
Like income or house prices, maybe? Lots of smaller values, few huge ones.
Exactly, those kinds of things. Applying np.log1p can pull those extreme high values in, making the distribution more symmetrical, more bell-shaped. This often helps linear models, or models assuming normality, learn better.
So a function transformer lets me apply log1p just like I'd apply standard scalar.
Precisely. You wrap np.log1p in a function transformer and stick it in your pipeline. It's especially powerful when dealing with data sets that have mixed data types, where maybe only some numerical columns need a log transform, while others need standard scaling. You can target it easily within a column transformer, which we'll get to later.
That function transformer sounds like a real Swiss Army knife for custom numerical tweaks.
It really is. Very versatile.
Now, staying with numerical data, I've heard about polynomial features. It sounds intriguing, but why would I want to create more features from my existing ones? Doesn't that just add more complexity, potentially confuse the model?
It's a fantastic question, and it gets to a deeper point about modeling capabilities. Polynomial features generates a new feature matrix by creating all polynomial combinations of your existing features up to a specified degree.
Combinations, like what?
So if you have two features, let's call them A and B, and you set degree 2. Polynomial features will keep your original A and B, but it will also generate new features. A squared, A2, B squared, B2, and crucially, the interaction term A times B, AB.
Ah, the interaction term. That seems important.
It often is. It represents how the two features influence the outcome together. Plus, it usually has a bias term, a column of all ones.
Okay, but why do this? Why add A2, B2, A?
Because it allows models to learn nonlinear relationships between your features and the target variable you're trying to predict.
Nonlinear, even with a simple model.
Yes. And this is the aha moment. Even fundamentally linear models, like standard linear regression, which just fits a straight line or plane,
Right.
can learn curved or complex relationships if you feed them the right kind of curved input features. By giving the model A2, you allow it to fit a parabolic relationship with feature A. By giving it AB, you allow the effective A to depend on the value of B.
So you're basically pre-processing the data to add nonlinearity so the linear model can then pick up on it.
Exactly. It's like giving a simple line drawer the ability to sketch complex shapes just by providing it with the right pre-drawn curves A2, B2, and interaction templates EB to combine. It dramatically increases the expressive power of linear models.
That makes a lot of sense. But I've also heard people argue that creating too many polynomial features, especially with high degrees, can lead to overfitting really quickly. Is that a risk?
That is absolutely a valid concern, and you're hitting on a classic trade-off in machine learning, the bias variance trade-off.
Right.
Yes, adding polynomial features, particularly if you use a higher degree, like 3 or 4, or if you start with many original features, can cause the number of generated features to explode very quickly. This significantly increases the model's complexity.
And complexity leads to overfitting risk.
Precisely. An overly complex model might fit the training data perfectly, essentially memorizing it, including its noise, but then it performs poorly on new unseen data because it hasn't learned the general underlying pattern.
So how do we balance that? How do we get the benefit of nonlinearity without just making the model memorize?
It comes down to thoughtful application and, crucially, proper validation. You wouldn't just blindly throw degree 3 at every dataset. Often, degree 2 is a good starting point, a sweet spot, providing useful nonlinearity without completely exploding the feature space.
Okay.
And critically, you'd use techniques like cross-validation. You train and evaluate your model on different subsets of your data to assess whether adding these polynomial features genuinely improves the model's generalization performance, its ability to predict on unseen data, or if it's just making performance on the training set look good while hurting real-world performance.
So test if it actually helps on data it hasn't seen before.
Exactly. It's about careful experimentation, monitoring performance on a holdout validation set, and perhaps using regularization techniques like Ridge or Lasso with linear models, which penalize large coefficients and can help control the complexity introduced by these extra features. It's about finding that optimal balance.
Makes sense. One more numerical one. Discretization. What's that about?
What?
Binning things.
Yes, exactly. Discretization, which scikit-learn implements with Cabin's discretizer, partitions continuous features into discrete intervals or bins. It's also known as quantization or binning.
Like taking age and putting it into buckets. 0, 10, 11, 20, 21, 30, etc.
Precisely that. You take a continuous variable like age or maybe cholesterol level and divide its range into a predefined number of bins, n-bins. Each original value then gets assigned to one of these bins.
Why would I want to do that? Lose information, surely.
You do lose some granularity, that's true, but it can be useful for several reasons. Sometimes it can make models more expressive or robust to outliers. More commonly, it helps with interpretability. It might be easier to understand a model's rule if it says if age is in 2130 then, rather than if age 20.73 and age 30.12 then.
Ah, okay. Simplifies the rules.
It can, yeah. It effectively converts a continuous attribute into a nominal categorical one. And importantly, once features are binned, they can then be treated like categories.
Meaning you could then, one hot, encode the bins.
Exactly. You could take the age bin feature with values like bin 1, bin 2, bin 3, and apply one hot encoder. So a single continuous age column could become, say, 5 or 10 binary columns, each representing an age range. This can sometimes be beneficial for linear models or other models that might struggle with continuous ranges, or, as mentioned, purely for making the feature representations simpler to reason about.
Wow, okay. That's an incredibly comprehensive toolkit, just for handling numerical data scaling, custom functions, adding nonlinearity, binning.
It really covers a lot of ground.
But what about those other kinds of data? The non-numeric stuff. We touched on it, things like gender, city name, product category. computers don't speak human language, right?
Right.
They absolutely need numerical representations to understand and process that kind of information.
Yeah.
How do we convert that qualitative non-numeric data into something a machine learning model can actually use effectively?
You're absolutely right. Categorical attributes need sensible numerical representations. We can't just feed text labels like mail or London or electronics directly into most algorithms.
So what's the first approach?
The first, and perhaps simplest conceptually, is ordinal encoding.
Ordinal, like order.
Exactly. This method assigns a unique integer to each unique category. So maybe red becomes 0, green becomes 1, and blue becomes 2. Or small equals 0, medium 1, large equals 2.
Seems straightforward.
It is. Scikit-learn has ordinal encoder for this. However, there's a major potential pitfall here.
Yeah. What is it?
By assigning these integers, 0, 1, 2, it can unintentionally induce an artificial order or magnitude that doesn't actually exist in the real-world relationship between the categories.
So,
A model might incorrectly interpret blue, value 2, as being somehow twice as important or greater than green, value 1, or that the distance between red and green is the same as between green and blue, if that ordering isn't intrinsically meaningful.
like with colors, red isn't less than green.
Precisely. If the categories are just nominal, names without inherent order, this arbitrary numerical ordering can confuse the model and potentially harm its performance. It's only really appropriate if your categories truly do have a natural, meaningful order, like your small, medium, large example, or maybe education levels, high school, bachelor's, master's.
Okay, so ordinal encoder is risky if there's no real order. What's the alternative for things like colors or city names?
This leads us to one-hot encoder, which is generally the preferred method for categorical features that don't have a natural, meaningful order, nominal categories.
One-hot encoding. I've heard that term a lot. How does it work?
Instead of assigning a single integer, one-hot encoder creates new binary columns with only zeros or ones for each unique category present in the original feature.
A column for each category.
Yes, and for any given data point, row, only one of these new columns will have a 1, indicating that row belongs to that category, and all the other new columns for that original feature will have a 0.
So it's hot in only one spot.
Exactly, that's where the name comes from. So if your original column had red, green, blue, red might transform it to 1, 0, 0, 0, green into 0, 1, 0, blue into 0, 0, 0, 1.
I see. Each category gets its own switch, on or off.
Perfectly put. This neatly avoids the false ordering issue of ordinal encoding. It gives each category its own independent representation without implying any kind of magnitude or ranking between them.
That seems much safer for nominal data. Does it create a lot more columns?
It can, yes. If you have a categorical feature with many unique values, like, say, ZIP code with thousands of possibilities, one-hot encoding will create thousands of new columns, which can lead to a very wide, sparse data set. This is sometimes called the curse of dimensionality in this context.
So there are trade-offs again. Handle high cardinality categories carefully.
Definitely. There are other encoding techniques for high cardinality features, like target encoding or hashing encoding, related to feature hasher, but one-hot encoder is the standard baseline for nominal data.
Okay. Now, you mentioned ordinal encoder for features. Is there something similar just for the target variable, the thing we're trying to predict?
Yes, there is. For encoding the target label specifically, your Y variable and classification tasks, scikit-learn provides label encoder.
Label encoder. How is it different from ordinal encoder?
Functionally, it does something similar. It assigns a unique integer between 0 and k1, where k is the number of distinct classes, to each unique target label. For example, if your target variable y contains cat, dog, cat, bird, label encoder would transform it into something like 0, 1, 0, 2.
So it also assigns integers. What's the key difference then?
The key difference lies in their intended input shapes and use cases. Ordinal encoder is designed to work on the features, your X matrix, which can be multidimensional, multiple columns. It expects a 2D array and can encode several categorical feature columns at once. Label encoder, on the other hand, is specifically designed to work only on the single-dimensional target variable y. It expects a 1D array or list.
So ordinal encoder for feature matrix X, label encoder strictly for target vector Y.
Exactly that distinction. You wouldn't typically use label encoder on your features, and you wouldn't use ordinal encoder on your 1D target vector.
Got it. Okay, so label encoder for targets gives integers. What if I need a binary representation for the target, maybe for certain model types?
Good question. If you need to convert multi-class target labels into a binary matrix format, often for use in one vs all or one vs rest classification strategies, Label Binarizer is the tool.
Label binarizer. Sounds like one-hot encoder, but for labels.
It's very similar in output. Yes, if you have labels like 1, 2, 6, 1, Label Binarizer would transform this into a matrix where each unique label gets its own column, and a 1 indicates the presence of that label for the row. So you might get 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 0, assuming 1 maps to call 0, 2 to call 1, 6 to call 2.
Okay. When would I need this? Don't most classifiers handle multi-class targets directly now?
Many modern estimators do, yes. You might not need Label Binarizer if your chosen classifier, like logistic regression or random forest classifier in Sklern, already supports multi-class targets directly. But it's useful if you're working with a fundamentally binary classifier and want to adapt it to a multi-class problem using that one vs all approach, where you train one binary classifier per class.
Right, training class A vs not A, class B vs not B, etc.
Exactly. Label Binarizer gives you the binary target format needed for each of those sub-problems.
Okay. What about really niche situations? Like what if a single data point can belong to multiple categories simultaneously?
Yeah.
Like a movie being both action and comedy.
Multi-label classification. Yes, Scikit-learn has a tool for that too. Multi-label binarizer.
Multi-label binarizer. Makes sense.
It extends Label Binarizer for scenarios where each sample can be associated with 0, 1, or multiple labels. If your input is something like a list of sets, say action, comedy, action, thriller.
Right, representing 3 movies with their genres.
Multi-label binarizer will create a binary matrix where each column corresponds to a unique genre found across all movies: action, comedy, thriller. A 1 in a cell indicates that the movie row has that genre column. So the output would look like 110 hashtag action comedy, 010 hashtag comedy, 101 hashtag action thriller.
Very cool. Handles that many-to-many relationship cleanly.
It does. Very useful for tagging problems, genre classification, topic modeling, etc.
Okay, one last encoding-related thing. I remember seeing add dummy feature. What's that for? Sounds trivial.
It seems simple, but it has a specific important purpose in some contexts. Add dummy feature does exactly what its name suggests. It augments your data set by adding an extra column where every single value is 1.
Just a column of ones. Why?
Its primary purpose is to provide a term for the bias or intercept in certain linear models, like linear regression or logistic regression, especially when implemented from scratch or using certain libraries.
The y-intercept in y-emps plus b. That b.
Exactly that b. If you represent your linear model using matrix multiplication, y equals xw, where x is features and w is weights, adding a column of ones to x allows the model to learn a corresponding weight in w that acts as the intercept term b. It ensures the fitted line or plane isn't forced to pass through the origin, 0, 0.
So it lets the model learn an offset. Do I always need it with scikit-learn models?
Often not explicitly with scikit-learn's high-level models like linear regression or logistic regression. By default, they usually have a parameter like fit intercept true, which handles this internally without you needing to add the dummy column yourself. But it's good to know about, especially if you're working with lower-level components or specific formulations where it might be required.
Okay, good to understand the principle. That covers a massive amount of ground on transforming features.
It's a lot, but it forms the core of preparing data.
Absolutely. So let's assume we've done all this. We've extracted features, handled missing values, scaled our numbers, encoded our categories. Our data is now this pristine numerical powerhouse ready for modeling. But what if we have too much of a good thing?
The dimensionality problem.
Right. What if not all those features we carefully prepared are actually helping our model? Or even worse, what if some are just adding noise, making it harder for the model to find the real signal? This brings us to the crucial optimization challenges of, well, feature selection and dimensionality reduction. How do we trim the fat?
Excellent question. Because you're right, more features isn't always better. The rationale behind feature selection is quite compelling. Not all features contribute meaningfully to predicting the target variable.
Some are just irrelevant.
Some are irrelevant, some might be redundant, highly correlated with other features providing similar information, and some might even introduce noise that confuses the model. Removing these less useful or harmful features has multiple significant benefits. Firstly, it can significantly decrease the size of your dataset, which means less storage space, less memory needed for processing. Secondly, it reduces computational cost. Training the model and making predictions becomes faster with fewer features. Thirdly, and often very importantly, it can lead to models that are more efficient, more robust, less prone to overfitting on noise, and sometimes even more interpretable because you're focusing on the truly important drivers.
Makes sense. Simpler models are often better. So how do we select the best features?
There are broadly two main categories of feature selection methods available in scikit-learn: filter-based methods and wrapper-based methods.
Filter and wrapper. Okay, what's the difference?
Filter-based methods select features based purely on their intrinsic statistical properties, looking at each feature and its relationship with the target variable independently of any specific machine learning model you might use later. They act like a pre-processing filter.
Okay, give me an example of a filter method.
A very simple but effective one is variance threshold.
Variance threshold. Sounds like it looks at how much a feature varies.
Exactly. This method removes features whose variance doesn't meet a certain threshold. By default, it removes features with zero variance.
Meaning the feature has the same value for every single sample.
Precisely. If a feature never changes, it contains absolutely no information that can help distinguish between different data points or predict different outcomes. It's completely useless for the model. So, variance threshold is a quick and easy first step to prune away these entirely uninformative constant features. You can also set a higher threshold to remove features with very low variance, though that requires more domain knowledge.
Okay, that's basic cleanup. What about more sophisticated filters?
Then we have univariate feature selection techniques. Univariate means they consider each feature one at a time. This family includes tools like select best, select percentile, and the more general generic univariate select.
How do they work?
These methods select features based on univariate statistical tests. They calculate a score for each feature independently, measuring how strongly that single feature relates to the target variable.
What kind of scores or tests?
Common scoring functions depend on the task. For regression, predicting a continuous value, you might use F statistic, ANOV F value, or mutual inf regression. For classification, predicting categories, common choices are chi2, chi-squared statistic, or mutual infoclassif.
Mutual information. What's that?
Mutual information is neat. It measures the dependency between two variables, in this case, a feature and the target. It's non-negative, and a value of 0 means the feature and target are completely independent. Higher values indicate a stronger relationship, whether linear or nonlinear. Chi-squared, on the other hand, specifically measures dependence between non-negative features and categorical class labels. Both MI and chi-squared are often recommended for sparse data.
Okay, so these methods score each feature's relevance to the target. Then what?
Then you use a selector to pick based on those scores. Select K-best simply keeps the K features with the highest scores. So if you set K10, it keeps the top 10 features and discards the rest.
Straightforward.
Select percentile is similar, but instead of a fixed number K, you specify a percentage. It keeps the top, say, 20% highest scoring features.
It's also clear.
And generic univariate select provides a more flexible framework allowing you to choose different modes for selection, like K-best, percentile, or based on statistical significance thresholds like FPR, FDR, FDU, combined with your chosen scoring function.
What's the main advantage of these filter methods?
They are generally very fast to compute because they only look at each feature individually. They don't involve training any complex models.
And there's a disadvantage.
The main disadvantage is that they ignore feature interactions. A feature might look weak on its own, low score, but could be very powerful when combined with another feature. Filter methods miss this. They also select features without considering the specific model you'll eventually train. The best features, according to a statistical test, might not be the best features for, say, a random forest model.
Right, which leads us to the other category, wrapper methods.
Exactly. Wrapper-based methods address these limitations. They are distinct because they wrap the feature selection process around an actual estimator, a specific machine learning model.
So they use the model itself to help pick the features.
Precisely. They evaluate subsets of features based on how well the chosen model performs using those subsets. This makes them more computationally intensive because they involve training the model multiple times, but they often lead to better performance because the features are selected specifically for the model you intend to use.
Okay, What are some wrapper methods?
A very popular one is recursive feature elimination, or RFE.
Recursive elimination. It sounds like it removes things one by one.
It does. RFE works by first fitting your chosen estimator, say a linear regression or an SVM, on all the initial features. Then it looks at the importance assigned to each feature by that model, ARG. the coefficients in linear regression or feature importances in a tree model.
Yeah, okay.
It finds the least important feature based on that ranking, removes it, and then refits the model on the remaining features. It repeats this process recursively, eliminating the weakest feature at each step, until only the desired number of features, and features to select, is left.
Wow, that sounds thorough but potentially slow if you have many features.
It can be, yes, as it refits the model many times. There's also a variation called RFECV, where the CV stands for cross-validation.
Ah, cross-validation.
Right. RFECV automatically finds the optimal number of features to keep by performing RFE within a cross-validation loop. It evaluates the model's performance on the held-out folds for different numbers of selected features and picks the number that gives the best cross-validated score, so you don't have to guess how many features to select.
That sounds very useful. Takes the guesswork out.
It's very powerful, yes.
What else is in the wrapper toolkit?
Another excellent wrapper-based approach is select from model.
Select from model. Does what it says.
Pretty much. This method selects features based on the importance weights obtained after an estimator has been trained on all the features. You train your model once, get the feature importances like COEF for feature importances, and then select from model filters the features based on these importances.
How does it filter?
You can set a threshold. It will keep only features whose importance is above that threshold. Or you can specify max features, and it will keep the top and most important features.
So it's like RFE, but without the recursive elimination part. Train once, then select.
Essentially, yes. It's generally faster than RFE because it only requires training the model once. A great strategy here is to use an estimator that inherently performs some kind of feature selection through regularization, like lasso, linear regression with L1 penalty, or a linear SVM with an L1 penalty.
L1 regularization. Remind me what that does.
L1 regularization adds a penalty to the model's loss function that is proportional to the absolute value of the model's coefficients. This has a fantastic side effect. It actively encourages the coefficients of less important or redundant features to become exactly zero.
It zeroes them out, like built-in feature selection.
Exactly. It performs feature selection as part of the model training process. So after training a lasso model, you can use select from model with a tiny threshold, like 1E5, to automatically pick only those features whose coefficients were not shrunk to zero by the L1 penalty. It's a very elegant and efficient approach.
Okay, cool. Okay, any other major wrapper methods?
There's also sequential feature selection, or SFS.
Sequential, like RFE.
Similar in concept, but it works differently. SFS selects or deselects features one by one in a greedy manner, aiming to find the best subset based on model performance. It has two main modes.
It starts with 0 features. In each step, it adds the single feature that provides the best improvement to the model's performance, evaluated using cross-validation. It continues until the desired number of features is reached.
Starts with all features. In each step, it removes the single feature whose removal hurts the model's performance the least, or improves it the most if removing noise. It continues until the desired number of features remains.
Forward adds, backward removes. How does it compare to RFE?
SFS can sometimes be slower than RFE or select from model because it typically evaluates more models, testing the addition removal of each feature at each step. However, it has a key advantage. It doesn't require the underlying estimator to expose feature importance attributes like COEF or feature importances. RFE and select from model rely on those. SFS just needs the model to have a score method like accuracy or R-squared, making it applicable to a wider range of estimators.
Ah, so more broadly applicable. Potentially slower. Trade-offs again.
Always trade-offs. The choice between forward and backward SFS also has efficiency implications. If you have 100 features and want to select the best 10, forward selection in 10 steps is likely much faster than backward selection 90 steps. Conversely, if you want to select 90 features, backward selection 10 steps is faster.
Right. Choose the direction that takes fewer steps. Okay, this covers a lot about selecting the most useful features from the ones we have, but
Yeah.
You mentioned dimensionality reduction earlier. Is that different from feature selection?
Yes, it's a distinct concept, though the goal is similar, reducing the number of features. Feature selection keeps a subset of the original features and discards the rest. Dimensionality reduction, on the other hand, transforms the data into a new, lower dimensional feature space. It creates new features that are combinations of the old ones.
So not just picking features, but creating new compressed ones. That sounds like a different kind of magic, almost like data compression, but for features.
It's not magic, but it certainly feels incredibly powerful sometimes. And you're right, it is like a form of intelligent data compression for your feature set. The most prominent technique here, a real cornerstone of unsupervised learning, is principal component analysis, or PCA.
PCA. Heard of it. How does it work? What's the intuition?
PCA is a linear dimensionality reduction technique. At its heart, it uses a mathematical operation called singular value decomposition, or SVD, to project your data from its original high-dimensional space down onto a lower-dimensional subspace, while trying to preserve as much of the original information, specifically the variance, as possible.
Okay, projecting onto a lower dimensional subspace while preserving variance. Break that down for me.
Imagine your data points scattered in, say, a 3D space, 3 features. PCA tries to find a new set of axes within that space. The first new axis, called the first principal component, PC1, is chosen such that when you project all your data points onto this single line, the spread variance of those projected points is maximized. It's the direction that captures the single largest amount of variation in your data.
So it finds the main direction of spread.
Exactly. Then PCA finds the second principal component, PC2. This second axis must be orthogonal, meaning perpendicular, or statistically uncorrelated to the first PC. And among all possible orthogonal directions, it's chosen to capture the maximum remaining variance.
So it captures the next biggest chunk of information, independent of the first.
Precisely. And if you were in 3D, the third principal component, PC3, would be orthogonal to both PC1 and PC2, capturing whatever variance is left. The crucial takeaway is that PCA effectively finds these new orthogonal axes, the principal components, that best represent your data's inherent spread or structure, ordered by how much variance they explain.
How does this reduce dimensions then?
Well, often the first few principal components capture the vast majority of the variance in the original data. Maybe PC1 captures 70% and PC2 captures 20%. Together, those first 2 PCs capture 90% of the original variance. So instead of keeping all your original features, say 100 of them, you might decide to keep only the first 2 principal components. You transform your data by projecting it onto just these 2 new axes.
So my 100-dimensional data becomes 2-dimensional.
Yes, you've reduced the dimensionality drastically from 100 down to 2. But because these 2 PCs were chosen to capture the most variance, this new 2D representation still retains about 90% of the essential information or structure from the original 100 dimensions.
That's amazing. What's the benefit?
Huge benefits. It makes data much easier to visualize. You can plot 2D or 3D data. It significantly speeds up training subsequent machine learning models because they're working with far fewer dimensions. It can sometimes even improve model performance by removing noise. The later principal components often represent noise rather than real signal, so discarding them can act as a form of noise reduction, and it helps combat the curse of dimensionality.
How do you use it in scikit-learn?
You use the sklearn.decomposition.pca class. The key parameter is n-components. You can set this to an integer, like n-components2, to keep the first 2 PCs, or perhaps more usefully, you can set it to a float between 0 and 1, like n-components 0.95. This tells PCA to automatically keep however many principal components are needed to explain at least 95% of the original variance.
Oh, that's handy. Let it figure out how many are needed.
Exactly. PCA is an incredibly valuable tool for handling high-dimensional data sets, visualization, noise reduction, and preparing data for further modeling.
Fantastic. Okay, so we now have this arsenal of individual tools. Cleaning, scaling, encoding, selecting, reducing dimensions. Each one sounds powerful on its own. But if you're like me listening to all this, you're probably thinking, how on earth do I keep track of all these steps?
Yeah, it gets complex.
Right. What if I need to, say, impute missing values first, then scale the numerical features, then maybe apply PCA, and then train my final model? And critically, how do I make absolutely sure I apply that exact same sequence with the exact same parameters every single time, especially when I get new data later for making predictions?
Yeah.
That just sounds like a recipe for mistakes and endless headaches.
You've hit on perhaps the most critical practical challenge in building robust, real-world machine learning systems, and the answer is pipelines.
Pipelines. Okay.
Data preprocessing, as we've seen, often involves applying multiple transformations sequentially. You might impute, then scale, then maybe add polynomial features, then select features, before finally fitting your model. The absolute non-negotiable rule is that you must apply the exact same sequence of transformations, using the exact same parameters, like the mean calculated by the imputer or the scaling factors from the scaler, which were learned from the training data only.
Right. Learned only from training data.
You must apply these consistently to your training data, your evaluation or validation data, and ultimately to any new unseen test data that you want to make predictions on.
What happens if you don't? if you mess up the sequence or use different parameters.
You introduce what's called distribution shift or data leakage. Your model sees new data that's processed differently than the data it was trained on. It might be on a different scale, have different features encoded differently, or missing values handled inconsistently. This leads to incorrect predictions and wildly unreliable performance evaluations. Your model might look great in testing, but fail miserably in production.
Yikes. Okay, so consistency is paramount. How do pipelines help?
Without pipelines, you'd be manually transforming your training data, saving the intermediate steps or the fitted transformers, then manually applying those same steps to your test data. It's not just tedious, it's incredibly error-prone. You might forget a step, apply them in the wrong order, or accidentally refit a transformer on the test data, which is a huge no-no data leakage. It leads to messy, hard-to-maintain code and lots of duplication.
Been there, done that. It's painful.
Exactly. This is precisely where scikit-learn's pipeline class becomes your best friend. Sklern.pipeline. Pipeline constructs a composite estimator. Think of it as a single object that bundles together multiple steps. It elegantly chains multiple transformers together and, optionally, can end with a final estimator like a classifier or regressor.
So it bundles the whole sequence.
Yes. Its primary purpose is to assemble all these pre-processing and modeling steps into one cohesive unit. This unit can then be treated just like any other scikit-learn estimator. You can fit it, predict with it, and importantly, you can cross-validate the entire pipeline together, ensuring consistent application across all your datasets from beginning to end.
How do you actually create one?
It's pretty straightforward. You use the pipeline constructor, which takes a list of steps. Each step is provided as a tuple, stepid transformer object. The stepid is a unique descriptive name you give to that step, like imputer or scalar, and the transformer object is an instantiated scikit-learn transformer, like simple imputer or standard scalar.
So a list of name object pairs.
Exactly. There's also a helper function called makePipeline. It's a convenient shorthand where you just pass the transformer objects directly, and it automatically names the steps based on their class names, e.g. simply imputer, standard scalar. It's quicker for simple pipelines.
Okay. Is there a rule about what can go in a pipeline?
Yes, a key rule. All the intermediate steps in the pipeline, everything except possibly the very last step, must be transformers. That means they must implement both the fit method to learn parameters from data and the transform method to apply the transformation.
Like standard scale or simple imputer, PCA.
Exactly. The final step in the pipeline, however, only needs to implement fit. This is typically where your machine learning estimator, your classifier or regressor goes as it learns but doesn't necessarily transform data in the same way.
Got it. Transformers all the way, estimator at the end, optionally. What are the big advantages of using these?
The advantages are profound and really elevate your machine learning workflow. First, there's incredible simplicity and convenience. You define your sequence of steps just once when you create the pipeline object. Then you just call .fit on the entire pipeline with your raw training data. It automatically calls fit transform on the first step, passes the result to the second step's fit transform, and so on, finally calling fit on the last step, the estimator.
So it handles the whole flow internally.
Automatically and correctly. Then, when you want to make predictions on new data, like your test set, you just call .predict on the same fitted pipeline object. It automatically applies the transform method of each transformer step, using the parameters learned during training, before passing the final pre-processed data to the estimator's predict method. No more manual passing of intermediate data.
That alone sounds worth it. No more juggling intermediate arrays.
Absolutely. This directly leads to reduced code duplication and increased consistency. You define your pre-processing logic once inside the pipeline. Then you apply that exact same pipeline object to your training, validation, and test datasets. No more copy-pasting pre-processing code blocks and risking introducing subtle inconsistencies. It makes your code cleaner, shorter, and much less error-prone.
What about tuning? Does it help with hyperparameters?
Massively. This is a huge benefit. Joint parameter selection or joint grid search. You can use scikit-learn's hyperparameter tuning tools like grid search CV or randomize search CV directly on the entire pipeline object.
The whole pipeline. How does that work?
You can define a search space that includes parameters from any step within the pipeline. You just refer to the parameters using a special double underscore syntax, stepid parameter name. For example, if you have a step named Pico and want to tune its end components, you'd specify aching components in your grid search parameters. If you have a classifier step named AALF, for example, in SVM, and want to tune its C parameter, you use ALFC.
So I can tune the imputation strategy, the scaling method, the number of PCA components, and the classifier's hyperparameters all at the same time.
Exactly, all in one go. Grid Search CV will then intelligently try out all the combinations you specified, training and evaluating the entire pipeline for each combination using cross-validation. This ensures that your pre-processing steps are optimized in conjunction with your final model, not in isolation, which often leads to much better overall performance.
That is incredibly powerful, optimizing the whole system.
It really is. One more advantage: caching. For pipelines involving computationally expensive transformation steps, maybe complex feature extraction or dimensionality reduction, you can set the memory parameter when creating the pipeline. You give it a directory path.
What does that do?
It tells the pipeline to cache the results of intermediate transformer steps to disk. So, during a grid search, if the parameters for the early steps haven't changed, the pipeline can load the cached results instead of recomputing those transformations from scratch every single time. This can dramatically speed up your hyperparameter tuning process, especially for large datasets or slow transformers.
Wow. Okay, pipelines seem absolutely essential for any serious ML work. Consistency, convenience, joint tuning, caching.
They are truly the backbone of robust, reproducible, and efficient machine learning workflows in scikit-learn. They enforce best practices and save you from countless potential errors.
I'm sold. Now, pipelines are great for managing a sequence of steps, but what if my data needs different types of processing applied to different parts of it? You hinted at this earlier, like maybe some columns are numerical and need scaling, while other columns are categorical and need one-hot encoding. My data isn't always uniform. How do we combine transformations when different columns need different handling within the same dataset?
Another excellent point, because that heterogeneous data scenario is extremely common. This is where composite transformers become absolutely invaluable. They allow you to apply different transformations to different subsets of your data and then combine the results. The star player here is column transformer.
Column transformer. Okay, sounds promising.
Column transformer is designed precisely for this situation. Its core function is to apply different lists of transformers, which could be individual transformers or even entire pipelines themselves, to different subsets of columns in your input data, which could be a NumPy array or, very conveniently, a pandas data frame.
So I can say, apply this scalar to columns A and B and apply this encoder to column C.
Exactly that. You provide column transformer with a list of tuples. Each tuple contains a name for the transformation block, the transformer or pipeline to apply, and crucially, a list or selector specifying the columns that transformer should be applied to.
How does it handle the output? Does it give back separate pieces?
No, and this is key. Once each transformer block has processed its designated columns, column transformer intelligently concatenates their outputs together side by side into a single unified output matrix.
Ah, so it does the processing in parallel on different column subsets and then stitches the results back together.
Precisely. This is essential because, as you noted, real-world data sets rarely consist of just one type of feature. You'll commonly have numerical columns needing scaling and imputation, alongside categorical columns needing one-hot encoding. Column transformer allows you to define these distinct pre-processing pipelines for different column types and apply them correctly, outputting a single matrix ready for your model.
Can you give a concrete example?
Sure. Imagine a simple data set with two columns: weight, numerical, and gender, categorical, male-female. You could set up a column transformer like this. One transformer block, num scalar, standard scalar, applies scaling only to the weight column. Another transformer block, Kate encoder, one hot encoder gender, applies one hot encoding only to the gender column. When you fit and transform this column transformer on your data, the output matrix will have. When you fit and transform this column transformer on your data, the output matrix will have. The first column containing the scaled weight values. When you fit and transform this column transformer on your data, the output matrix will have. The next two columns containing the binary output from one hot encoding gender. For example, one column for is female, one for is male. When you fit and transform this column transformer on your data, the output matrix will have. So your original two columns become three columns in the final processed output, all neatly arranged.
That's incredibly useful for mixed-type data. Handles the branching and merging automatically.
It's a cornerstone of modern scikit-learn pre-processing, especially when working with pandas data frames, where you can select columns by name.
Is column transformer the only tool for combining things?
There's also feature union. It works slightly differently. While column transformer applies different transformers to different columns, Feature union applies a list of transformer objects in parallel to the same input data or specified parts, and then concatenates their outputs side by side into a potentially much larger matrix.
Applying multiple transforms to the same data in parallel. When would you do that?
It's useful for creating combined feature representations. For example, maybe you want to apply PCA to your data and also apply some univariate feature selection, and then combine the results of both into one feature set to feed to your model. Feature union lets you run the PCO transformer and the select-best transformer independently on the input data, and then it stacks their outputs horizontally.
So it's for combining different types of feature extraction or transformation on the same input.
Exactly. It allows for building very complex and flexible preprocessing workflows, often used within or alongside Kalman Transformer and Pipeline to structure sophisticated feature engineering pipelines.
Okay, that makes sense. One more specific case.
Yeah.
What if the variable, I'm trying to predict the target variable itself, needs some kind of transformation? Maybe it's heavily skewed.
Ah, yes. Sometimes transforming the target variable poorly can actually help your regression model perform better. This is where transform target regressor comes in.
Transform target regressor. Okay.
This is a specialized composite transformer, specifically a meta-estimator that wraps around a regression model, like linear regression or ridge. Its purpose is to transform the target variable before fitting the wrapped regressor.
Why transform the target?
Many regression models, particularly linear ones, perform best when the relationship between features and the target is roughly linear, and when the model's errors, residuals, are normally distributed. If your target variable has a very skewed distribution, like house prices, often skewed right.
Right. Lots of medium prices, a few mansions.
Right. Exactly. Transforming the target, often using a logarithm, np.log, or perhaps a Box-Cox transformation, can make its distribution more symmetrical, more normal-like. This can linearize its relationship with the features and stabilize the variance of the errors, helping the underlying regression model learn more effectively and satisfy its assumptions better.
So transform target regressor applies, say, log to y before training the regressor.
Yes. It takes two main arguments: the regressor you want to use and a transformer, or func and inverse func, to apply to y. It fits the transformer on y, transforms y, then fix the regressor using the original x and the transformed y.
But then the predictions will be on the transform scale, right? Log dollars isn't very intuitive.
Good point. And transform target regressor handles this automatically. When you call .predict on it, it first gets the prediction from the underlying regressor, which will be on the transform scale, for example, log dollars. Then, crucially, it automatically applies the inverse transformation, ng, the exponential function np.8xp if you used np.log, to map the prediction back to the original scale of the target variable.
Oh, that's clever. So you get the modeling benefit of the transformation.
Yeah.
But the final predictions are back in the original interpretable units.
Precisely. It manages the forward and inverse transformation of the target variable seamlessly around the regressor. It's a very neat way to leverage transformations for potentially better regression performance without complicating the interpretation of the final output.
Fantastic. Okay, we've covered an immense amount of ground on preparing and transforming data. It feels like we've got the tools to handle almost anything. But there's one final, very common and really critical pitfall I want to touch on, something that happens a lot in real-world data. What happens when some outcomes, some classes you're trying to predict, are just super rare compared to others?
Ah, the imbalanced data problem.
Exactly. When your data is inherently imbalanced, for instance, in fraud detection, maybe 99.9% of transactions are legitimate and only 0.1% are fraudulent. Or in medical diagnosis, a rare disease might appear in only 1% of patients. How do we ensure our models don't just ignore these crucial rare cases? How do we stop them from becoming totally biased towards the overwhelmingly frequent majority class?
That's a fundamental challenge, and you're right, it's pervasive in many critical real-world applications. Fraud detection, anomaly detection, disease screening, defect detection in manufacturing, churn prediction, the list goes on.
So what is the core problem with imbalanced data?
The core problem is that standard machine learning algorithms are often designed, implicitly or explicitly, to optimize for overall accuracy across all samples. When one class vastly outnumbers the others, the model can achieve very high overall accuracy by simply always predicting the majority class.
Like the fraud example. Predict not fraud every time, get 99.9% accuracy, but completely fail at the actual goal.
Exactly. The model appears successful based on the standard accuracy metric, but it's completely useless for the task it was intended for, catching the rare but critical events. This bias towards the majority class happens because the model gets rewarded more during training for correctly classifying the abundant majority samples than the rare minority samples. This leads to models that overestimate the majority class and severely underestimate or even completely ignore the minority class.
So standard accuracy is misleading here. What should we do instead?
First, you need to use appropriate evaluation metrics that do account for imbalance, things like precision, recall, sensitivity, F1 score, AUC, area under the ROC curve, or precision recall AUC. These give you a much better picture of how well the model is performing on the minority class, which is often the class you actually care most about.
Okay, better metrics. But how do we actually fix the model's bias during training?
There are several approaches. One major category involves resampling the data to create a more balanced training set before training the model. This is often done using the excellent Imbalance Learn library, which integrates well with scikit-learn.
Resampling, like changing the number of samples.
Yes, there are two main flavors, undersampling and oversampling.
Okay, what's undersampling?
Undersampling involves reducing the number of examples in the majority class, or classes, to make it closer in number to the minority class. A common technique is random undersampler from MLP. It simply randomly discards samples from the majority class until a desired balance is achieved, often 1.1.
So if I have 1,000 not fraud and 10 fraud, it might just keep 10 not fraud samples.
Exactly. It would randomly select 10 of the 1,000 not fraud examples and discard the other 990, leaving you with a balanced data set of 10 fraud and 10 not fraud.
Seems simple, but aren't you throwing away a ton of data?
That's the major drawback. You are literally discarding potentially valuable information from the majority class. This can be problematic, especially if your data set isn't huge to begin with, as the resulting model might not learn the characteristics of the majority class well enough, or it might become too sensitive to the specific minority samples that remain. There are more sophisticated undersampling methods that try to be smarter about which majority samples to keep or remove, but random undersampling is the simplest.
Okay, so undersampling shrinks the data set, risks losing info. What's the alternative? Oversampling.
Correct. Oversampling takes the opposite approach. It increases the number of examples in the minority class or classes to match the majority class.
How does it increase them? Just copy the existing ones.
That's one way. Random oversampler from MLP simply makes random copies of existing minority class samples until the desired balance is reached. So in our 1,000 versus 10 example, it might make 99 copies of each of the 10 fraud samples, or pick randomly with replacement, to create 990 new fraud samples, resulting in a balanced data set of 1,000 not fraud and 1,000 fraud.
Does copying them over and over cause problems, like overfitting to those specific examples?
It can, yes. Because you're just duplicating existing samples, the model might overfit to those specific instances and not generalize well to slightly different minority class examples it hasn't seen.
So is there a smarter way to oversample?
Yes, and this is where a very popular and often more effective technique comes in, SEMOT, which stands for a synthetic minority oversampling technique.
SEMOT, synthetic samples. How does that work?
Instead of just copying existing minority samples, SEMOT intelligently generates new synthetic examples for the minority class. It works like this. For each minority sample, it finds its k-nearest neighbors that are also in the minority class. Then it synthesizes new samples by interpolating between the original sample and its chosen neighbors. Essentially, it creates new minority samples along line segments connecting existing ones in the feature space.
So it's creating plausible, new minority examples that are similar to existing ones, but not identical.
Exactly. This provides the model with more diverse examples of the minority class, rather than just exact copies, which often helps it generalize better and reduces the risk of overfitting compared to simple random oversampling. SMOT usually leads to better model performance on the minority class.
SMOT sounds pretty clever. Are there other approaches besides resampling?
Yes, there are other techniques too. Some algorithms allow you to adjust class weights directly, for example, setting class weight balanced in many scikit-learn classifiers, which tells the algorithm to pay more attention to mistakes made on the minority class during training. There are also specialized algorithms designed for anomaly detection or cost-sensitive learning. But resampling, especially oversampling with SMOT, or sometimes combinations like SMOT followed by some undersampling, is a very common and effective first step.
And it's crucial to do this before training.
Absolutely crucial. An imbalanced data set, if not handled appropriately either through resampling, class weighting, or choosing the right metrics and algorithms, can lead to models that seem to perform well on overall accuracy, but are actually ineffective, biased, or even unfair when you look at their performance on the critical minority classes. So addressing imbalance is a vital step for achieving meaningful, effective, and fair model performance in many real-world scenarios.
Wow. Okay, so stepping back and looking at everything we've discussed, what does all of this mean? We've really taken a deep dive, haven't we, into the expansive pre-processing toolkit that scikit-learn offers.
We certainly have.
We've traced the journey, really, from that raw, potentially messy data all the way to a format that's digestible for complex algorithms. We've covered those crucial initial steps, feature extraction, handling those pesky missing value.
Imputation.
Right. Standardizing and normalizing numerical data, expertly encoding categorical features, intelligently selecting the most impactful features using filters and wrappers.
And dimensionality reduction with PCA.
Yeah. And then we explored the powerful glue that holds it all together, building robust and repeatable pipelines, including handling those diverse feature types with column transformer and even transforming target variables.
And wrapped up with the critical strategies for tackling imbalanced data sets.
Exactly. Which, as we discussed, is such a common and often overlooked real-world problem. It truly shows how much foundational work, how much craft, happens way before the supposed magic of machine learning training even begins.
It really does. And if we try to connect all this to the bigger picture, it's important to remember, I think, that these tools, these techniques we've discussed, they're not just about manipulating numbers to fit into an algorithm's input requirements.
Right, it's more than just formatting.
Much more. They are fundamentally about transforming raw, messy, incomplete reality into a structured, comprehensible format. A format that allows these powerful machine learning models to truly learn from the data and hopefully generate meaningful insights or accurate predictions. It's really about bridging that gap between the chaotic, often imperfect real world and the precise computational power we have at our fingertips today.
That's a great way to put it, bridging the gap.
And thinking about that bridge, it raises an important forward-looking question, doesn't it? As data becomes even more complex, more diverse, thinking of unstructured text, images, audio, video, graph data, streaming data, how will these pre-processing techniques need to continue to evolve to keep pace? What new challenges will we face in making sense of it all and preparing these increasingly complex data modalities for machine learning? The journey of data preparation is never truly finished. It's a dynamic and evolving field in its own right, constantly adapting to the ever-increasing complexity and scale of the data we want to learn from.
That is a fantastic and really thought-provoking point to leave you, our listeners, with. The world of data pre-processing is indeed vast, it's intricate, and as you just heard, it's constantly evolving. It's often where the majority of the effort, and frankly, where a lot of the success or failure of a machine learning project lies.
Absolutely.
We sincerely hope this deep dive has given you a solid foundation, demystified some of these crucial scikit-learn tools, and maybe sparked your curiosity to explore them further in your own learning journey or your next project. Until next time, keep digging deep.